Welcome to this session. In the previous two sessions, we have seen the concept of generating functions, and we have also seen how to decompose our fractional expressions by using the method of partial fraction decomposition. Now it's the time to put them all to use together in solving the recurrence relations with the help of generating functions. So let's start. Just a quick recap of what a generating function is. Say for example, if I have a series a0, a1, a2, a3 and so on, then the generating function for the series is given by a0 plus a1t plus a2t square plus a3t cube and so on, and is designated by g of t. In the summation notation, I can write it as summation from r is equal to 0 to infinity ar t to the power r. In the previous session, we have seen how to find out the generating function of some common series. Some of the generating functions are listed in this table. This table actually lists the general term of the sequence versus the generating function. One generating general term 1 indicates that the generating series is 1 comma 1 comma 1 comma 1 comma 1. This is actually indicating the nth term or the kth term. The second series is actually 1, 2, 3, 4, 5, 6, 7, 8. Remember, the series actually starts from A0. We are starting the series from 0. So k plus 1 means the series is starting from 1, 2, 3, 4, 5, 6 and so on. Whereas this particular series k is actually 0, 1, 2, 3, 4, 5, 6, 7 and so on. So this is a table of the most commonly used generating functions, right? We'll be using them as we go on solving the recurrence relation using the generating functions. I'll show you the table once again, but this is the table we'll be referring most commonly. So let's jump directly into the numerical problems. So let's take this numerical problem. ar plus 2 minus 3ar plus 1 plus 2ar is equal to 0 under the initial conditions a0 is equal to 2 and a1 is equal to 3. Now we have to solve this recurrence relation with the help of method of generating functions. So we'll first multiply this equation with t to the power r and sum it from 0 to infinity. Now this step is very important. Please make a note of how to sum it. See, there are two different types of recurrence relation that are normally given to us. The first type of recurrence relation has ar plus 1 and ar plus 2. This is the type of recurrence relation where ar is the smallest subscript. And if ar is the smallest subscript, I'll sum it from 0 to infinity. See, my purpose is to make the smallest subscript a0. Why? Because a0 is the first initial term that is given to me. Right? Keep this in mind. So the first step is we'll multiply the equation with t to the power r and sum it from 0 to infinity. I get summation of r is equal to 0 to infinity ar plus 2 t to the power r. See, this is ar plus 2. Then 3 summation of r is equal to 0 to infinity ar plus 1 t to the power r plus 2 into summation of r to 0 to infinity ar t to the power r is equal to 0. Now we know that what we'll do is we'll expand it a little bit. So expanding this, see, remember r is starting from 0, but here I am having r plus 2. So what becomes a2 plus a3t plus a4t square and so on. Similarly here minus 3, this is r plus 1, so it becomes a1 plus a2t plus a3t square and so on. Once again, this is 2ar, so this becomes a0 plus a1t plus a2t square and so on. Right? So what I've done is I've simply expanded this series. Now what I want to convert this expression in terms of my generating function. So what I'll do, we know that gt is equal to a0 plus a1t plus a2t square and so on. So what I'll do is I'll write each of these expressions in terms of my generating function. See, we manipulate the above equations to obtain the expressions in terms of g. Say for example, let's take this example. I'm showing you one step. a2 plus a3t plus a4t square. Now what I can do is, See, in my generating function expression, a2 is usually the coefficient for t square. So to make it so, what I am doing is I am multiplying this expression by t square and dividing it by t square. So this becomes a2 t square plus a3 t cube plus a4 t4 divided by t square. Now what I will do is, see, the generating function expression has the two terms a0 and a1t before this. So what I will do is I will add these two terms and then I will subtract these two terms. So the original expression will essentially remain the same. So now this expression a0 plus a1t plus a2t square plus a3t cube and so on, now this expression is now equal to my gt. And minus a0 minus a1t, I'll keep as it is. So this becomes g of t minus a0 minus a1t divided by t square. So this a2 plus a3t plus a4t square and so on now becomes gt minus a0 minus a1t upon t square. Similarly, if I were to take this expression a1 plus a2t plus a3t square, see, a1 is the coefficient for t over here. So what I'll do is I'll multiply this by t and divide it by t, and as I'm missing a0, so I'll add a0 and subtract a0. This is actually same as my generating function. So I'll be left with this was the original expression. It will be converted into g of t minus a0 minus a1t upon t square. This will be g of t minus a0 upon t, and this will be gt. Now all I have to do is I'll have to simplify this expression, substituting initial values. See, remember the initial values were given to us, a0 is equal to 2 and a1 is equal to 3. These were the initial values that were given to me. So now I substitute the initial values. So it becomes gt minus 2 minus 3t minus 3 gt minus 2 upon 2 t, and 2 gt is equal to 0. So we solve it, it becomes g of t minus 2 minus 3t minus t 3 gt minus 2 plus t square 2 gt, right? T square, I am multiplying this entire expression by t square on both sides. On the right hand side, 0 multiplied by t square will be 0. Open it up, it becomes g of t minus 2 minus 3t minus 3t gt plus 6t plus 2t square, g of t is equal to 0. I take the terms which contain g of t on one side, it becomes 1 minus 3t plus 2t square, and the other terms are 2 minus 3t is equal to 0. So g of t becomes 2 minus 3t divided by 2t square minus 3t plus 1. Now this is the expression. Now I have to decompose it using the partial fraction method. So I'll use the partial fraction decomposition. I'm not showing you over here how to decompose it using partial fractions. I hope you all know how to do it. If there are any issues, if you have any confusions or problems, you can refer to the earlier video, right? I've given you a video on how to use the partial fraction decomposition. So by using partial fraction decomposition, 2 minus 3t divided by 2t square minus 3t plus 1 becomes 1 upon 1 minus t plus 1 upon 1 minus 2t. So now g of t, see over here, g of t was equal to 2 minus 3t divided by 2t square minus 3t plus 1. Now g of t has become, this expression is now equal to this expression. So g of t is now equal to 1 upon 1 minus t plus 1 upon 1 minus 2t. Now I will use this table. See, 1 upon 1 minus t is similar to this one. 1 upon 1 minus 2t is similar to this one. So here, if my expression is 1 upon 1 minus t, then the general term of the sequence is 1. If it is 1 upon 1 minus 2t, then the general term will be equal to 2 to the power k. See, it's a over here, t is the variable over here, x is the variable over here, does not make any difference, but this is the coefficient, the a, so here the coefficient is 2. So using the table, we get gt is equal to summation of now this is the nth term. So this becomes summation of r is equal to 0 to infinity art to the power r. This 1 upon 1 minus t becomes 1 to the power r, t to the power r from here, and this becomes 1 minus 2t becomes 2 to the power r, t to the power r from here. Now what I can do is simply I'll cancel the summation, I'll cancel the t to the power r, and I'll be left with ar is equal to 1 to the power r, that is 1 simply, right, and 2 to the power r. See, what I've done is I've cancelled the summation from all the three, and I've cancelled t to the power r. See, t to the power r is present in all the three, so I can divide both sides by t to the power r. So I'll be left with ar is equal to 1 to the power r plus 2 to the power r, and 1 to the power r I know is 1, so ar is equal to 1 plus 2 to the power r. This is the solution to the required recurrence relation. Now let's take another example. ar minus 7ar minus 1 plus 10ar minus 2 is equal to 0, right? So once again we'll begin in the same manner. Multiply the recurrence relation by t to the power r and sum from 2 to infinity. Now please pay attention. We have summed it from 2 to infinity, as the smallest subscript over here is ar minus 2, and I want to make it as a0. Why? Because the initial value is given as a0. So what I'll do is I'll start it from 2. So it will be r is equal to 2 to infinity ar t to the power r minus 7 r to 2 to infinity ar minus 1 t to the power r plus 10 summation of ar minus 2 t to the power r. Next, I'll simply expand it. So as this is now going from r is equal to 2, so that it becomes a2 t square, a3 t cube, a4 t4, and so on, minus 7. So this is r minus 1. When r is equal to 2, this becomes 1. So a1 t square plus a2 t cube, and so on. And this is 10, a0 t square plus a1 t cube, and so on. I'll once again write it in the form of gt. So we know gt is equal to a0 plus a1t minus a2t square. So I'll rewrite these expressions in terms of gt. Now taking this section, for example, I have a2t square plus a3t cube plus a4t to the power 4. Now if I take this section and compare it to the expansion of gt, you'll see that a2t square is already over here, and the further terms like a3t cube and so on, they are already present over here. What is missing is the terms a0 and a1t. So this expression, if I take a2t square plus a3t cube and so on, so what I can do is I can simply add a0 plus a1t over here and then subtract a0 and a1t from here. So this expression essentially will remain the same. But now this portion of the expression is now a representation of gt. So this now becomes gt minus a0 minus a1t. Similarly, if I take this expression a1t square plus a2t cube and so on, and if I compare it over here, I see that a1 is the coefficient of t square in the given expression, whereas in gt this is the coefficient of t. So if I take t common from here, so I get a1t plus a2t square and so on, which is similar to the expression for gt, except that it is missing the term a0. So what I can do is I can add a0 over here and subtract a0 over here. So now this expression is mimicking the expression for gt. So I have 7t gt minus a0, right? This a0, when I add it over here, I am not subtracting it from here. So now this becomes 7t gt minus a0. So this expression now essentially becomes gt minus a0 minus a1t minus 7t gt minus a0 plus 10t square gt. So simplifying it, I get, if I open it up, gt minus a0 minus a1t minus 7t gt plus 7 a0t and so on. If I collect all the terms from with gt 1 minus 7t plus 10t square minus a0 minus a1t plus 7 a0t, putting in the initial values a0 and a1 both are equal to 3. So I get this expression gt 1 minus 7t plus 10t square minus 3 minus 18t is equal to 0. So gt is equal to 3 minus 18t divided by 1 minus 7t plus 10t square. Now once again applying the method of partial fractions, this now becomes equal to 4 upon 1 minus 2t minus 1 upon 5t. So this is gt is equal to this expression. Once again doing the same thing, I'll use the table over here. See, 1 minus 2t is similar to 1 minus ax, 1 minus 5t is once again similar to 1 minus ax. So using the table over here, gt is equal to 4 into summation of r is equal to 0 to infinity 2 to the power r t to the power r, and 1 minus 5t becomes 5 to the power r t to the power r. Once again, I'll cancel the summation and t to the power r from both the sides. So I'll be left with 4 into 2 to the power r minus 5 to the power r. That is the required solution. Right? Let's take another example. an minus 5an minus 1 plus 6an minus 2 is equal to 3 to the power n. Now this is a slightly different example. Here this is a non-homogeneous expression. So once again, as this is n minus 2, so we'll multiply it by x to the power n and sum from 2 to infinity. So this is the expression I'll get. N is equal to 2 to infinity an xn, n is equal to 2 to infinity a n minus 1 xn and a n minus 2 xn. And on the right hand side, once again, I have 3 to the power n xn. Once again, what I'll do is I'll expand it. a2x square plus a3x cube and so on, a1x plus a2x cube and so on, plus 6a0x square plus a1x cube and so on. On the right hand side, I have n is equal to 2 to infinity 3 to the power n x to the power n. Right? If I take 3 square x square common from here, 3 square x square common from here, I get from n is equal to 2 to infinity, I get 3 to the power n minus 2 and x to the power n minus 2. Remember, I have taken 3 square and x square outside of the entire summation series. Now let us put n minus 2 is equal to k, so that when n is equal to 2, k is equal to 0, and obviously when n is equal to infinity, k is going to be infinity. Why? Because infinity minus 2 is nothing but infinity. So this now becomes, this expression now becomes 3 square x square, k is equal to 0 to infinity, 3 to the power k, x to the power k. And once again, we'll use the table. If you remember, the table tells me that this is equal to 1 minus 3x, 1 upon 1 minus 3x. So I'll show you the table once again if you want. See the table over here. If I have a to the power k, if this is the general term, then this is the function 1 minus ax. So I have g0 this. On the right hand side, I now have 9x square upon 1 minus 3x. 3 square x square is 9x square. Right? So gx 1 minus 5x plus 6x square minus 2x is equal to this. So once again, what I have done is I have put in the initial values. a0 is equal to 0 and a1 is equal to 2 over here. So I get gx 1 minus 5x plus 6x square is equal to 9x square upon 1 minus 3x. This 2x I take to this side. So this now becomes 3x square plus 2x upon 1 minus 3x. 1 minus 5x plus 1 minus 6x square, I can decompose it to gx 1 minus 5x plus 6x square can be factorized to 1 minus 2x, 1 minus 3x. So I take it to this side. So this becomes gx is equal to 3x square plus 2x divided by 1 minus 2x, 1 minus 3x square. Right? So applying the partial fractions, this becomes equal to 7 upon 1 minus 2x minus 10 upon 1 minus 3x plus 3 upon 1 minus 3x square. So once again, using the table, this is equal to summation of n is equal to 0 to infinity a n xn, 7 2 to the power n xn minus 10 3 to the power n xn plus 3 n plus 1 into 3 to the power n xn. Cancelling the summation n x to the power n. So I get 7 into 2 to the power n minus 10 into 3 to the power n plus 3 n plus 1 3 to the power n, which can be solved as 7 into 2 to the power n plus 3n minus 1 3 to the power n, which is the required solution. Let's take a last example. This is the recurrence relation to be solved. Remember, see over here, the smallest subscript is r. So what I'll do is I'll multiply t to the power r and sum from 0 to infinity. So this is what I'll get. If I multiply it by t to the power r and sum it from 0 to infinity, expand it, I get this solution. Right? On the right hand side is once again 2 to the power r, t to the power r. So simplifying LHS in terms of GT and using GF table on right hand side, 2 to the power r. See, I have the general term 2 to the power r, t to the power r. So this is 1 minus 2t. I'll use the same method as I have discussed in the earlier examples. So this now becomes gt minus a0 minus a1 t upon t square minus 2 gt minus a0 upon t plus gt is equal to 1 upon 1 minus 2t. Simplifying it, I get gt, if I simply multiply t square on both sides, so I get gt minus a0 minus a1t minus 2t gt plus 2t a0 plus t square gt is equal to, on the right hand side, using the initial values, I get gt 1 minus t whole square minus 2 minus 3t is equal to t square upon 1 minus 2t. Solve it. It becomes gt 1 minus t whole square is equal to t square upon 1 minus 2t plus 2 minus 3t. Solving it, I get this expression. Now using the partial fraction method, this is equal to 1 upon 1 minus 2t plus 1 upon b upon 1 minus t plus c upon 1 minus t square. By partial fractions, a is equal to 1, b is equal to 3 and c is equal to 2. So gt is equal to 1 upon 1 minus 2t plus 3 upon 1 minus t plus minus 2 upon 1 minus t square. Once again, what I'll do is I'll use this table. 1 minus 2t gives me 2 to the power r, t to the power r. 1 minus t gives me 1 and 1 minus t whole square gives me k plus 1. So this is r plus 1. Simplify it. So you get this expression 1 plus 2 to the power r minus 2r, which is the required solution. Now I suggest you solve as many questions as possible, because this takes a lot of practice. Once you practice, I am sure you will be able to solve the recurrence solutions with the help of generating functions very easily. Till the next time, thank you.